In 2007, the mayor of the small German town Staufen decided to do his part for the environment. He approved a drilling project to heat the old city hall with hot water from underground. The drilling began in early September and went 140 meters deep. About 2 weeks later, the first walls began to crack. The cracks became deeper. Buildings were evacuated. Then they were torn down. Then the lawsuits began. Oh, and they elected a new mayor. Geothermal energy could solve our energy problems if we just dig deep enough. But how much can geothermal energy realistically help with reaching net zero? What new technologies are being developed? And what the hell happened in Staufen? That's what we'll talk about today. All planets in the solar system, including Pluto, formed from the same ball of hot plasma as the Sun. The major difference between our Sun and the planets is that it's larger, and because the Sun is larger, its gravitational pressure can sustain nuclear fusion. Smaller clumps of matter, like our Earth, can't do that, so they cool. And before you know, you have people driving around in pickup trucks with bumper stickers complaining about the government. But it takes a long time for a planet to cool. Therefore, Earth is really still a ball of this hot plasma, just that it now has a crust on the outside where it's already cooled. But when you dig, it gets warmer, and the deeper down you go, the warmer it gets. Scientists believe that the temperature at the Earth's core doesn't just come from this initial heat of the plasma, but comes partly from radioactive decay. But no one knows exactly because no one's been there, probably because the center of Earth is about as uncool as it gets. The temperature at the core of Earth is an estimated 5,000 to 7,000 degrees Celsius. That's about the same as the surface of the Sun and my office in the summer. But we don't need thousands of degrees. A few hundred degrees Celsius are sufficient to boil water and drive turbines with it. Such temperatures can be found in a few kilometers depth in most places on Earth. Just how deep you have to dig for that depends strongly on the location. In some places one doesn't have to dig at all because steaming hot water bubbles out of the ground. On the Azores they make stew by lowering it down into a hole and cooking directly with geothermal heat. In Reykjavik they heat the roads in the winter with geothermal heat. But in most places it isn't that easy. Geoscientists estimate that the total energy reserves in the upper 10 kilometers of Earth's crust are about 10 to the 27 joule. The total global energy consumption per year is at present about 5 times 10 to the 20 joule. This means if energy demand remained stable, geothermal energy would last several 100 million years. You may suspect that it isn't terribly realistic that we exploit all this energy, and you'd be right. But a somewhat more realistic evaluation comes from the US Department of Energy. They refer to geothermal energy as America's untapped energy giant and estimate that the generation of electric energy from geothermal sources in the US has the potential to increase from presently about 3.5 gigawatts to more than 60 gigawatts by 2050. Then it'd provide 8.5% of the total US electricity, which is a refreshing change from securing energy supply by invading other countries. And this is only for using geothermal energy for electricity generation. Estimates are even more impressive if you include direct use, that is heating with geothermal heat. Researchers from the National Renewable Energy Laboratory claim that every house in the US could be heated from geothermal sources for millennia. This sounds good, but in reality, geothermal energy presently plays a small role in most places on Earth. In 2020, the total global power capacity of geothermal was about 15 gigawatts. This is about 1% of the worldwide installed solar capacity, or 0.2% of the total. The world leader in total geothermal energy production is currently the US, but that's mostly because it's a big country. If you look at the numbers per capita, the world leader is, no surprises, Iceland. In Iceland, geothermal sources deliver a whopping 66% of the primary energy. That's more than 6 megawatts per person and far ahead of the next big geothermal nation, that is Sweden, with less than a tenth of that. Here you see an illustration of a geothermal power plant in Iceland, which is pretty straightforward. Pump down cold water, get hot steam back up, cool the steam and extract energy from it, repeat. This is the Krafla power plant, and these are some images from Iceland just for relaxation. Carbon dioxide emissions for most geothermal power plants are low, according to the IPCC comparable to those of solar power, but in contrast to solar power, geothermal sources deliver 24/7, 365 days a year. And while some plants release sulfur dioxide from underground, it's a fairly small amount and it can be filtered out. Geothermal energy isn't expensive either. As you see in this figure, levelized cost of electricity from geothermal power plants is currently comparable to that from solar and wind. This might make you think geothermal energy would be expanding rapidly, but not so. The global trend in the past 5 years doesn't differ from the trend in the previous decades, and it's pretty much linear. Though in some countries the expansion of geothermal has picked up, that's Turkey, Indonesia, Kenya and the USA. The issue with geothermal energy is that while it works very well in some places, these places are rare. This figure shows the geothermal resources in the US. As you can see, there's much more potential on the West Coast, and America is a geothermically lucky part of the world. This figure shows the global potential for geothermal energy. The redder, the better, and I swear this is not a political statement. What this means is that in many places you have to dig deep, not just into the ground, but also into wallets. Indeed, if you look at this figure again, you'll see that while the costs for solar and wind have been dropping, the costs for geothermal and hydropower have been rising, and basically for the same reason. The best places have been taken long ago, and now the returns are diminishing. Costs of a geothermal plant are heavily weighted towards early expenses, while the operating costs are comparable to those of solar and wind. Geothermal wells are often more than twice as deep as oil wells, and the drilling accounts for more than 50% of the total costs. For example, in the US, drilling a 4-kilometer hole costs about $5 million. For 10 kilometers, the drilling cost skyrockets to $20 million per hole. By the way, the deepest hole ever drilled is the Kola super-deep borehole in Russia near the border of Norway. It reached 12,262 meters in 1989. According to an urban legend, the Russians working on the project announced they drilled into hell and wanted nothing more to do with it. Whatever the reason, they put a lid on the thing and didn't reopen it, and no one's ever broken the Russian record. So what can we do to get more geothermal energy into the grid? Well, for one thing, we can try to make it more affordable. One reason the drilling is so expensive is somewhat surprisingly not actually the equipment, it's time. According to a 2015 paper by a group of American researchers, what makes the drilling so expensive is that when things don't go as planned, because something breaks or something leaks or the ground isn't as expected, the entire crew must sit around and wait on site. The costs for this are tens of thousands of dollars a day, whether those people work or not. This means planning plays a big factor for bringing down the costs. The oil and gas industry has a big advantage in that because they've built expertise going back more than a century. But geothermal is also expensive because things break and must be replaced, like drills and stuff. This means there are 3 major ways to make geothermal energy work better. Better preparation and management, better methods to find and exploit sites, and better ways to drill. How do you prepare people for drilling? Well, of course, by teaching them physics. Yes, physics. In 2020, 2 researchers from Texas developed a training program for managers of drilling operations, teaching them things about rocks and cracks and stuff. This cut down the drilling time into half and significantly reduced the cost. Quite amazing what a little physics can do. But then I may be biased. Another way of preparing is to do more studies of the ground and what the drilling does to it. Many projects on this are currently underway. For example, the GeoVision project in the US, and the European Union has a similar project called GeoEnvy. But leaving aside issues with management and training, there are physical reasons why geothermal drilling is more challenging than drilling for oil. You have to dig deeper and the rocks get hot, really hot. A particularly relevant factor for efficiency of a geothermal power plant is an obscure physical quantity called the specific enthalpy of water. Enthalpy measures how much energy a substance can carry. It's a function of environmental conditions like temperature and pressure. The thing is now that the enthalpy of water at around 200 times atmospheric pressure increases rather suddenly at 374 degrees Celsius. Above that temperature, the water is called supercritical. This doesn't mean it'll start commenting on your hairstyle. It means it's neither a liquid nor a gas, but both at the same time. Supercritical water can carry several times more energy per mass, and the conversion to electric energy becomes more efficient. Taken together, this increases the energy output by up to an order of magnitude, which is really impressive. Drilling companies call their holes wells. More than 25 geothermal wells have encountered temperatures above 374 degrees, but so far none of them have been used for energy extraction for an extended amount of time. The issue is, it's difficult. In the 1970s, the Italians drilled a hole in Tuscany that would have been suitable for a supercritical power plant. But these wells aren't only hot, the hot rocks also contain a lot of unpleasant chemicals. Those make the water that's used for drilling highly acidic, which wrecks the equipment. Even if you don't use water, you have acidic gases bubbling up. In this case, the drill pipe corroded and broke, and the well had to be abandoned soon after drilling. The Italians tried again with a second hole. It blew up. In 1981, in the United States, they tried to tap onto a supercritical reservoir, but drilled into high-pressure steam that caused the casing to collapse. This well, too, was abandoned. 1988, in Iceland, they just about prevented the same thing from happening by quickly dumping a lot of gravel down the hole. In 2003, they tried again near Reykjavik, but the hole became blocked for unknown reasons and was abandoned. Then there was the Iceland Deep Drilling Project. The first plan in 2009 was to drill to 4.5 kilometers depth. However, just beyond 2 kilometers, they drilled into magma that plugged the lowest 2 meters of the hole. Gases began bubbling up. The surface equipment experienced significant corrosion, which eventually led to a failure of the main valve. The well was shut down. They drilled a second hole in 2014, which encountered the same problem: acidic gases that wrecked the equipment. They did, however, test this well for more than 1 year and found it to be capable of producing more than 36 megawatts. The third deep well of the Iceland Deep Drilling Project is planned for the next few years. As you see, geothermal isn't for the faint-hearted. Next thing you can do is help nature along by creating geothermal sites rather than using existing ones. These are called enhanced geothermal systems. The American company Alterock Energy, for example, uses a beam of microwaves to drill small holes, crack rocks, and then clog the cracks with a biodegradable substance. This prevents the water from seeping into the rocks, so they can drill even deeper and create an extended network of cracks through which water can then be circulated. The company says it's a cost-effective and efficient way to get thermal energy out of many rocks that otherwise wouldn't lend themselves to water circulation. They have a test site in Newberry, Oregon. And then there are better drills. The UK-based company Hydrovolve launched last year what they call the GeoVolve Hammer. Instead of just rotating the drill, they also hammer with it, which is called percussive drilling. Their device is plug and play and adapts to the environment. They claim that this is less damaging to the drill, can speed up drilling by up to 10 times, and cut costs by half. Researchers from France and the UK are developing another new drilling technique that adds a high-pressure water jet. The idea is to use the water to cut the rock into particular shapes, so it can then be more easily broken by fluid-powered percussive hammers. The researchers claim that this technique will drill rocks more than twice as fast as current technologies, and that it would reduce costs by up to 65%. So far, they only have computer simulations and lab tests, but they expect to have a real-world prototype by 2024. Another method that was presented by Japanese researchers uses water to give the rocks thermal shocks by sudden heating and cooling, also known as summer in the UK. This cracks the rocks a bit, so they are then easier to drill. They are currently making test drills down to some dozen meters and are filing patents. A company called Petra uses a torch of gas at super high temperature, a plasma really, to drill rock thermically. They have a prototype and are currently testing it. And researchers from MIT want to combine a traditional rotary drill with a millimeter wave laser. They claim that this way they'll be able to drill 20 kilometers deep in just 100 days of drilling. They want to start drilling in 2024, and maybe then we'll figure out whether the Russians really found hell down there. And there's more to come. Last year, the US Department of Energy announced up to $20 million in funding to lower the cost of developing geothermal energy, so we'll probably hear a lot more about drills in the near future. So what happened in that little city Staufen? Germany has a lot of sediment layers, and predicting just what you'll find if you drill into the ground is extremely difficult. In this case, what happened is the following. The drill went through a Kuiper layer and into a reservoir that contained warm water under high pressure. The lower part of the Kuiper layer has a fairly high content of clay and shale. This has blocked off the water from the upper Kuiper layer for the past 200 million years or so. But now they drilled through it. The pressure drove the water up and it leaked into the upper part of the Kuiper layer. That Kuiper layer is mostly calcium sulfate. It reacts chemically with water to form a type of gypsum. Trouble is, the gypsum has a higher volume, so this entire layer, which is more than 100 meters thick, started to expand. This raised parts of the inner city, in some places more than half a meter. But it didn't raise the ground evenly, so the buildings began to crack. The same thing happened in several other cities in Germany. If that sounds scary, it's because it is. But the problem is rather specific. This Kuiper layer exists only in some parts of Europe. And now that the problem is on the radar, new drilling projects are watching out for it. But there are more general problems with drilling projects. Creating cracks in rocks for extended geothermal systems is quite similar to fracking, and it increases the risk of small earthquakes and blowouts. For example, last year operations at a geothermal project in Cornwall were temporarily stopped after seismic activity was detected. In April 2020, a well blowout was reported in Indonesia, and similar accidents have happened in Australia, Chile, and Japan. In 2021, a high-pressure burst of gas from a well from a geothermal project in Sumatra killed 5 and injured 24. And the drilling might not be the only problem. Researchers from Germany and Spain reported in 2019 that for supercritical reservoirs, earthquakes are also induced by the cooling of the rocks, which comes from the operation of the power plant. After all, its very purpose is to extract the heat. They use a computer simulation which shows that the rate of induced seismicity at the fault increases 4 orders of magnitude after 7 to 10 years of water circulation. The authors claim that this result suggests that the lifetime of supercritical geothermal projects is limited by cooling-induced earthquakes. One final thing to notice is that geothermal plants do emit greenhouse gases. That's because the fluid which they circulate carries carbon dioxide and methane and often a number of other nasty chemicals out of the ground. Just exactly how much depends on the ground, so it can be difficult to predict. Looking at a global average value is misleading for geothermal because the variation is so large. This figure, for example, shows the carbon dioxide emissions from several geothermal plants in Iceland. For reference, the average life cycle emissions of a natural gas power plant would be at about 500 grams carbon dioxide per kilowatt hour, and those of solar at around 40. There are some geothermal plants in Turkey and Italy that actually emit more carbon dioxide than natural gas power plants. So what do we learn from this? What I take away from this is that geothermal energy is at the moment underexplored and underfunded. There is a lot of potential in it that can be tapped onto with more research and better technology. It also seems to me, however, that these drilling operations are and will remain risky and for that reason also expensive. Like many other things we've been talking about, it isn't going to be a panacea for climate change, but it may make a contribution. This video was sponsored by my friend and colleague Brian Keating. Brian is an experimental physics professor at the University of California and leads some of the world's most exciting cosmology experiments. He's also an amazing podcaster and YouTuber. On his show, you get to hear the true experts like Neil Turok, Juan Maldacena, Jill Tarter, Sarah J. Penrose and Anna Ijas. He's so far hosted 14 Nobel Prize winners, plus astronauts like Chris Hadfield, science communicators like Dr. Becky, Fraser Cain, Neil deGrasse Tyson, and a handful of billionaires like Jim Simons, probably the world's smartest billionaire, and Michael Saylor, Bitcoin's greatest champion. I've been on his podcast a few times too. If long podcasts aren't your thing, Brian also has short explainer videos, similar to the ones I make, but from him you'll get the point of view of an experimentalist. This is why I'm subscribed to Brian's channel. You have to watch out what those experimentalists are up to. More seriously, check out Brian's channel and subscribe. You won't regret it. And Brian has a special offer for the next 200 people that subscribe to his newsletter. He'll send you a real-life piece of space dust, a real meteorite, when you sign up at briankeating.com/list. If you enjoy my channel, I'm sure you'll enjoy Brian's too. Thanks for watching. See you next week.